Our first speaker will be from Rush School of Perfusion. Her name is Alicia Walker, and she is talking about the design and adaptation of 3D printed heart valves and the teaching methods and the surgical planning of cardiac surgery.
Hi, everyone. First, I would like to thank Susan and everyone else here at Sanibel Symposium for allowing me the opportunity to speak and present my research here today. I've had a really awesome week here. As mentioned, my name is Alicia Walker. I'm a perfusion student at Rush University. Today, I will be presenting my research on refining teaching methods by 3D biofabricating cardiac structures for clinicians and students. So on today's agenda, I'll start with a bit of a background, then I'll go into what is 3D bioprinting, and then I'll talk about how we're incorporating 3D bioprinting at Rush University. When I began thinking about research topics a few months ago, I knew I wanted to do something that would be hands-on and interactive. When I heard that previous Rush students, Morgan Shoaf and Rabah Alawi, had been working with a 3D printer, I was intrigued. I'd always found 3D printers to be fascinating, although I didn't have any experience with them whatsoever. Due to my curious nature and my love for learning new things, I immediately knew that 3D printing was something that I would enjoy researching for my master's project while at Rush University. Not only that, with 3D printing rapidly evolving in use over the last decade, I love the idea that this technology is next generation and I could have a tangible effect while at Rush University. It wasn't too long ago that Adam Feinberg and his colleagues at Carnegie Mellon had 3D bioprinted the first full-size model of the human heart using the FRESH method, which stands for Freeform Reversible Embedding of Suspended Hydrogels. The purpose of the FRESH method is to 3D print biomaterial into a slightly denser gel and then wash away the gel bath so that you get a structure that is suturable, one that mimics the physiological characteristics of cardiac tissue in the sense of suture retention and compressibility. As I said, a previous Rush student had the opportunity to apply for a 3D printer workshop at Carnegie Mellon and go there to build the printer herself. After attending the workshop, they were able to bring it back to Rush, which we are lucky to have in use today. The 3D printer is important because it allows you to print a gel, like I said, into a slightly denser gel, which mimics the physiological characteristics of cardiac tissue. The gel-like fashion of the biomaterial is important because the gel you're printing would otherwise collapse into air. So here you can see this is what our lab looks like here at Rush University, where we do all our work, and the printer that was built and brought back to Rush. So now we'll go into what is 3D bioprinting. 3D bioprinters conduct the patterning and printing of bioink into a gel bath in order to create 3D models that represent living tissues or organs. Bioink may be composed of biomaterials such as cells or other biologics like sodium alginate that are spatially patterned to print models that represent living tissues or organs. Most common bioinks used include gelatin methacrylic, collagen, and sodium alginate, which we are using, and are deployed by extrusion, droplet, or a laser-based process. Advancements in biofabrication have led to the printing of human-like tissues and organs, such as heart valves, for educational purposes. Printing tissue-like models has allowed the opportunity for a more realistic simulation, where students may learn different techniques. These bioprinted materials, whether they be structures to educate with or a tool to use for surgical planning, could have a major impact on the quality of medical procedures provided in the future. At Rush University, we want to 3D bioprint these cardiac structures. We want to use the material that I mentioned, sodium alginate, which Carnegie Mellon claims to mimic the physiological characteristics of cardiac tissue in the sense of both suture retention and compressibility. So essentially, what we are doing, as you can see here in the picture, we will take a CT scan and convert them into an STL file, which are then sliced on a G code. In lay terms, essentially, we are using the CT scan, uploading it into our reconstruction software, and then isolating the structure and uploading it into our printer to print with the sodium alginate. This allows us to have a structure that is left over to use to improve teaching methods and plan complex cardiac surgeries. So you may be wondering, how do 3D bioprinted structures differ from traditional suturing methods? At Carnegie Mellon University, research experts in the biomechanical engineering claim that this fresh method may offer a more realistic representation of cardiac structures. This method is unique because it allows the possibility to print suturable 3D hollow structures, which others do not. Printing a gel into a slightly denser gel support bath yields a structure that would otherwise collapse in air. Simple features such as size, shape, and feel all allow for a more hands-on, real-life-like structure, and more complex features such as compressibility, suture retention rate, and more realistic spatial orientation interaction between the user and the conduit. So there's many benefits of working with these 3D biofabricated cardiac structures for perfusion medicine. This includes enhanced perfusion fellow education interaction, suturing practice, or sharing ideas about perfusion methods such as cannulation. It also has the potential to print patient-specific structures in complex cases. Along with that, the ability to learn from and demonstrate with defected patient-specific pathology. 2 different tests were conducted by Adam Weinberg and his colleagues at Carnegie Mellon. They found that these tests, suture retention testing and compression testing, both helped prove that it was lifelike to cardiac tissue. Here you can see in the image the suture test that they did with a printed block and a printed cylinder that allowed them to practice the suturing with the hook and that the gel would still hold together. These tests led to the conclusion that sodium alginate constructs mimic the mechanical properties of both cardiac tissue and are durable enough to handle, suture, and perfuse, making them ideal candidates to use as surgical training tools. So how are we incorporating the 3D bioprinting at Rush University today? As I mentioned before, this is what the printer looks like, along with the program software that we use to run the printer. As you can see where the arrows are pointing, there's a small needle that comes down off of the machine, and this is what the needle is used to physically print the structures in the gel that you see pictured in the bottom right corner. The purpose of our study is to measure the overall satisfaction of these 3D bioprinted cardiac structures and their educational use with surgical clinicians at Rush University. We want to print these 3D structures using the sodium alginate through the FRESH method and utilize these structures for the purpose of teaching students and clinicians to see how they compare to traditional suture methods. This could be compared to felt, cork, and/or plastic. The inclusion criteria for our study will include physicians, residents, fellows, or other PAs at Rush University, really anyone with knowledge and experience with suturing, and exclusion criteria being very limited or no surgical suturing experience, or surgical experts without cardiovascular surgery experience. The satisfaction will be measured using the response of a survey. This will consist of about 10 questions and will be considered if 50% or greater of the participants respond in an affirmative manner regarding the likability of the 3D bioprinted heart valves and structures. So some strengths and limitations of our project. Strengths, as I mentioned, the suturing of anatomically detailed models. Not only that, but the ability to print structures will provide a constant supply of cardiac structure conduits, which can be printed and available for the clinical teaching and practice. This also provides the potential to produce suture materials that mimic the pathological cardiac structures, and overall, this is pretty low cost to maintain this research. However, the limitation is that 3D bioprinting of these cardiac structures may be time-consuming, essentially because printing on this 3D bioprinter does require a good amount of operational training. Even for me, I just started this a few months ago, and there's definitely been a lot to learn, and there's a lot more to it than it looks like. In conclusion, personalization of 3D structures would benefit surgical planning, as well as institutional distribution of defective structures could standardize cardiac surgical simulation training. It can be concluded that 3D bioprinting of conventional or non-traditional cardiac structures, particularly pathological structures, would profoundly advance educational methods and clinical applications of cardiovascular medicine. New adaptations of bioprinting technology are emerging at a fast rate, and therefore equipment and processing materials are being designed and developed even further. The closer that research comes to developing implantable structures or medically approved therapies, the more important it is for researchers to really fine-tune their production methods. So what are we doing now? This has definitely all been a learning process and a journey for me over the last couple months. My research partner, Brendan, and I are hoping to continue to make great strides with our research over the next year at Rush University before we graduate, and continue to be an extension of Adam Feinberg and his colleagues' research. While the future of this technology is unknown, there is such a tremendous potential for new and undiscovered capabilities that 3D bioprinting applications could have on intra or perioperative surgical methods, and we are really excited to be a part of this. Thank you. I'm happy to take any questions or comments. I know there's only a couple minutes left here, but